Look, y'all, I know I haven't made a math video in a little bit, but look, I gotta relax sometimes. It's not really Regents review time yet. Like, once that actually comes around, I'll be posting all the videos. But see, I'm just making a few now, you know, to build up to it, you know. Alright, y'all, today we're talking about sequences. I know we've been talking about polynomials the last two videos, but we're taking a little break, just talk about sequences. And I'm gonna go over a Regents question later on in the video too, because, you know, why not? Now, by definition, a sequence is a function where the domain is positive integers.
What?
So the x value, which in this case, they normally go by n. You'll know what I mean. It'll be 1, 2, like all of that. And it has to be positive, meaning no zero and no negatives. You know, the definition doesn't matter when we actually like talk about them, but that is just what a sequence really is. We're going to talk about arithmetic sequences, geometric sequences, all the formulas that you're given about them on the Regents. And we're going to be talking about sigma notation. Ah, yes, my favorite thing in the world. You know, they named that after me, by the way. Like, they saw me and they decide, you know what?
Oh, brother, this guy stinks!
Now, an arithmetic sequence is a sequence that goes up at a constant rate. So let's say our first value is 1, and it's going up by 2 each time. Well, then the next one is gonna be 3. You know, all the odd numbers by the looks of it. It goes up by 2 each time. It's going up at a constant pace. See, that amount that it's changing by is called the common difference. All that is how much a sequence is decreasing or increasing by. In this case, it's by positive 2. If we're given this sequence and we have to find a common difference, we can see it's going down by 3 each time. So the common difference would be negative 3. Now, let me just explain what I meant by, you know, the whole sequences are just domains with positive integers thing. See, most sequence equations will show probably some random letter, in this case A, and it will be A sub n. Now, what n is the term in a sequence. If we plug in 1 for n, we're trying to find the first term. If we do 2, we're trying to find the second term. That's what it is. It must be, like I said earlier, positive integers. Now, with that out the way, let's talk about the recursive definition of arithmetic sequences. What those are arithmetic sequences where you find a term by using the previous one in the sequence.
I understand it now.
So an example of a recursive definition would be this right here. Yeah, I know my A's are looking a little chopped. We don't talk about it. We're given that a term is equal to the previous term in that sequence plus 4. See, if we were trying to find the 5th term and we plug in 5 for n, then we'd be using the 4th term because we do 5 minus 1. This would be A sub 4. Now you can see down here, like, that's not the whole equation. We're also given the first term. That's because if we aren't given any terms, we can't find, you know, the next ones in the sequence. And so you must always provide the first term when giving a recursive definition. I'm pretty sure I've seen a question like that in the Regents where you have to make something like this. And so let's take this case right here. We have this sequence. How about we turn that into a recursive definition?
No!
See, our first term here seems to be 1. So we can get the 1 part. We can say A sub 1 equals numero uno. Now for the actual definition, we obviously need, you know, A sub n for any term. And of course, we're doing recursive, so we need a previous term. And if we look, as we go up, we're adding 2 to get each one. To find 7, we're taking the third term, which is 5, and adding 2 to it, which is the common difference. So we would say A sub n minus 1 plus 2, meaning to find the recursive definition of an arithmetic sequence, you would take the previous term and add it to the common difference, where obviously if the common difference is negative, you'd be subtracting there, you know. So yeah, that should be all for that. Next up, we're talking about geometric sequences. Now these, they do not increase at a constant rate. Let's take this sequence, for example. This is a geometric sequence. This goes up by 2, but then that goes up by 4, and then that's by 8. It's not the same. See, these are different because instead of the common difference, like with, you know, the arithmetic ones, it goes up by a common ratio. Yeah, although this isn't being added by a specific number, it's being multiplied by a number, which we can see obviously is being multiplied by 2. That would be its common ratio. Now let's take this equation right here, which also, what type of definition is this? We just talked about it. If you said the recursive, that's correct. That's because it uses the previous term in the definition. If we look at the first few terms for this, we obviously for the first term is 1. The next one would be 4, then 16, 64. It's going up exponentially, which normally sequences definitely ties into exponential functions, but we're saving that for another video. That's a whole different thing. But yeah, that would be the difference between geometric and arithmetic. Now see, before we move on to the legendary sigma notation, let's talk about the given formulas for arithmetic and geometric sequences. See, recursive definitions are very inefficient. If you're given that and you have to find like the 15th term, you got to go through like all 14 that comes before it. And that is a pain, which is why you should worry less about that and more about the formula that's given to you for the Regents. You can see right here for arithmetic sequences, you have a of 1 plus n minus 1 in parentheses times the common difference d. Now obviously this is given to you and I already explained what these things mean, so I don't need to really go over it, but just know this is the formula for that. And for geometric sequences, you have a of 1 times the common ratio to the power of n minus 1. Notice how I talked about how, you know, it's kind of like an exponential equation where you can see the n value is in the exponent. But yeah, you don't have to memorize it. If you come across anything needing it, just go to the reference sheet. Now with that done with, let's move on to the good stuff. Here it is right here, the sigma himself. Also known as summation notation, which is definitely a better name for it, but you know, sigma notation is sigma, so. Oh, brother. Now see, what sigma notation does is it finds the sum of a sequence. See, let's say we see this random thing. Now this is a sigma notation fully stacked out with different letters and crap. The k squared is the sequence itself, and we're trying to find the sum of all of its terms between 1 and 3. So the first term we know is 1 squared, the next term in line would be 2 squared, and then it ends at 3, so our last one would be 3 squared. Do our math, we get 1 plus 4 plus 9, which should give us 14. It's not too hard to understand. We need to remember this is the lower bound and that's the higher bound. Now I want to go over another example just so we can, you know, get the hang of this. Also, I should note the letter that you see here, it doesn't matter what that letter is. It could be any letter. In this case, I'm just using K because, you know, I just feel like it. Now here we're trying to find the sum of the terms between 1 and 4 of this sequence. So we want to find the first term, which is just 1 over 1. We want to add it to the second term, 1 over 2. Adding to the third term, which is 1 over 3. And then the fourth term, 1 over 4. See, we're going to do some basic math here, you know, greatest common denominator or something. That should be 25 over 12. Looking at my notes, that should be the correct answer. See, nothing too crazy. And that leads me to my final topic of this video. Here is the sum of a finite geometric sequence formula. You use this to obviously find the sum of all terms going between the first term and whatever you plug in for n, which will be the highest term. We can see the common ratio here because this is specifically for geometric sequences, which I don't know why they don't got it for like arithmetics. Also, this is given to you on the Regents, thank goodness, because look at this mess. And I'm gonna go over a Regents question that actually screwed me over horrendously. Damn. That involves this. See, right here we got a question from the June 2023 Regents, and you can see it's question 24, and it's multiple choice, so that's nice. We're told that John and Margaret deposit $500 into a saving account, and they deposit $500 more every time the birthday hits, and we're given, it goes up to the 21st birthday, and we're given the rate too of 4%. So I thought it was an interest question. Now I knew these two options right here just weren't right, but I had no clue what to do. I was so bamboozled. I forgot sequences existed. I just crossed these off immediately. Truth was, I should have been crossing these off because for some reason it was a sequence question. Now just looking at these, you can see it's in the formula for, you know, the sum of a finite geometric sequence. See, if you look, it's exactly like it. So if this were written as a sequence, we obviously know the first term would be $500, which, you know, that helps us out with these ones. Now R, the common ratio, what is it going up by? Well, we're given that there's a 4% annual interest rate, which means by every year, by every term, it will be increased by 4%. See, let's just say our base thing is 100%. It doesn't go up or down. In this case, we're adding the 4% to that, which obviously gives us 1.04. That's what we're multiplying it by. And I'll put that to the 21st, which also I should put 21 here for n, because remember it says we're going to 21st birthday, and that does kind of look like a 5 too. Holy cow. Now already we can kind of stop. I mean, we don't have it written in the same way, but just look. They're obviously trying to trick us with the 0.04, and this shows 1.04, so we can just say it's 2 right off the bat. On the Regents, I would have been skedaddling off. I'm done now. But let's just keep going real quick. We got 1 minus the rate, 1.04. And hold on, let me rewrite this real quick, because what I'm about to do is a little weird, and the Regents, they really do love pulling some bull crap on you. Now, if we look here, we're wondering, what the heck? How did they do this? This doesn't make much sense. But what I think they did is they factored out a 500 just so they can make it look as different as possible. Because if we take out 500 from 500, we get 1. And if we take 500 from here, we just leave the rest, which is 1.04 to the power of 21. Bottom, it would be the same. We aren't doing anything down there. And now we have the exact form and answer choice 2. The Regents loves doing this, and it makes no sense. Like, that's such a weird step, and it's so inefficient. It's just to get, trick you. And that's really it for what I got today. Good thing I got sequences out the way. It's an annoying thing, and it definitely ties into exponential equations, which if you want a video on that, just let me know. I'll see y'all in my next video, which is hopefully going to be about radicals. Goodbye, guys.